Go ahead.
Oh, hello, everyone, and welcome to the first session of the last day of FSC 2022. And this is a session on stream ciphers. And the first talk is Fake Near Collision Attacks by Patrick Derbez, Pierre-Alain Fouque, and Victor Molimar. And Patrick is given the talk.
Thank you for the introduction. So this talk is about
Sorry.
Okay. Okay, so this talk is about fastener collision attacks, which is a cryptanalysis technique that was introduced at Eurocrypt 18 by Bin Zhang and his co-authors against the stream cipher grain V1, and another paper using the same techniques was published at EGCrypt 19. Sorry. So you can see in this table how this technique is powerful. Very amazing results. It breaks two stream ciphers, and we'll see how it does that. So basically, the core of this cryptanalysis technique is the refined self-contained method. So first, you will compute some differential table containing near collisions. That's what is in green here. And this table will be used in an algorithm, the blue one, to compute. So this algorithm takes as input a key stream, so some key stream bits here, KS, and a difference. So other inputs are not really relevant. But at the end of this algorithm, you will output a set X, which contain the value which generated KS with a good enough probability, okay? And so this is a random algorithm, heuristic algorithm. So at the end, you perform an amplifying phase in which you generate many set X and you take the union of the intersection of those sets, okay? And if you look at how they applied this technique, it's a bit suspicious. So in particular for grain V1, it was applied so on two rounds of the update function. Okay, so you apply the algorithm with 2 bits of key stream. And in this case, they are able to generate a set X which contain the right value, which much higher expected probability than expected. And what is very interesting with this application is that the function f here, okay, is actually can be written as a some linear part plus a function h. And so the technique is applied on the function h equals to 0. Okay, so it's like you applied it with the key stream equals to 0 and the function h. And so basically you restrict the search space without any knowledge of the key stream. So that was very suspicious. And you have same results for F51. And what is wrong? Why all of that is impossible? This is because of this very trivial theorem, which says that if you have an algorithm which takes as input a function f and an element of the image of f, and which output a subset of the pre-image of this element. And now if you draw uniformly at random an element of the pre-image of F, of this element, then the probability that this element belongs to X is exactly the size of X divided by the size of the pre-image. Okay, and the refined self-contained method fulfills this the requirements of this theorem. So the only possibility for the results of the fastener collision attacks to be true are if we cannot draw uniformly at random an element of the pre-image. So it means that there is a bias or distinguisher on the initialization phases of both grain V1 and A51. Okay. So obviously, this is not true. And we found several other problems in both papers. And what is very weird is that in both papers, they say that they performed a lot of experiments to check the results, while we just added a loop in the C code they provided, and we found that probabilities does not match what they say in those papers. Okay, so fastener collision attacks are a dream. And I think there are much more interesting things to do. For instance, yesterday I was walking through the city and I saw this theorem on a t-shirt. And I think it's much more interesting to think about it. Okay. Thank you for your attention.
Thank you very much, Patrick. Are there any questions? Some questions in the room?
Yes.
Yes. Online?
Yes. Yes. Hello. Yes, Patrick. Yes,
Hello,
I have
yes.
a question. Yes.
Yes.
Actually, yes. Can we go back to the next one?
Yeah. I will. I don't know why this is super. I have trouble hearing it, but I will say it to you later. Okay. So where do you want to go?
Actually, yes, I did not agree with Patrick's the conclusion. Actually, the concrete probability for the heating for each restricted interstate is determined by the value of the state, not the theorem 1. Actually, theorem 1 has nothing to do with this attack. I think there are some misunderstanding. Besides, I think the merged states in your paper is incorrect because each list can only be generated once and used once, but you counted twice. So this is a problem. I think there is a paper at InScript last year. You can see it.
I'm really sorry. Can you say exactly what is the question you have? Where is the problem? Because
yes, I think there are several problems about Patrick's paper. First, I would like to thank Patrick's interest. But after our communication, yes, by email, I think I can interpret very well the phenomena that you add a for loop in the public available code, because the concrete value, the concrete probability for the heating of each restricted state can be theoretically derived, and we can verify it by experiments, so that we can well explain this phenomenon. Besides, there is an error in your paper on the merging states, because each list can only be generated once and used once. But
I'm really sorry.
Paper,
I'm
yes.
sorry. I'm sorry. I have to cut you because we don't have a lot of time for questions, and I think this is not a question. It's more like if you have something concrete, please say it quickly, right? Because maybe there are some other questions in the room.
Yes. My basic conclusion is that except theorem 2, I did not fully agree with Patrick's talk and their paper.
Okay,
and
thanks for the comment.
Yes, we have all of them.
I'm sorry. We really don't have time. Okay. Are there any more questions in the room? Thank you. Any more questions in the room? No? Okay, I have one question about so what do you think would be left in the original papers of interesting after taking out?
Actually, I'm not really sure because there are a lot of math in this paper, and I don't see exactly what is wrong, but in my opinion, the whole technique is wrong. So
But
there is nothing left.
We have a lot of experiments to verify it. Yeah.
Okay.
Yes,
Okay.
Actually, I still do not agree. Yes.
Okay. Thank you. Are there any more questions? Okay, then we are going. Thanks a lot, Patrick. Let's thank Patrick again. And so the next talk, Christina. Sorry, do you know where?
Yeah. Can you hear me?
Yes.
Okay.
Yes.
I'll share my screen. Yeah.
But yeah, we don't see the slides yet. Ah, okay, sure.
Can you see my screen?
Okay, yes, perfect. So we are going to hear now the second talk of this session on automatic search of cubes for attacking stream ciphers. And the talk is given by Yao Sun. Thank you. You can start, yeah.
Okay. Hello, everyone. I'm Yao Sun. It's my pleasure to give a presentation here. My topic is automatic search of cubes for attacking stream ciphers. And first, let's see the main contribution of this paper. Our work is based on the cube attack, which has become one of the most powerful tools of attacking stream ciphers. By summing up the values of a Boolean function over a cube, we can obtain the superpoly of the cube. And the active value of the superpoly can be obtained in the online phase. And with the equation, we can filter out many illegal keys. Then how to generate the superpoly has become the first problem to be solved in the cube attack. And this problem was finally solved by the C-subset division property without unknown subset. So, so what is the next problem to be solved in the cube attack? And in my opinion, I think it is how to find good cubes or superpolies. Clearly, linear superpolies are perfect, but they are hard to find. So we turn to search for a special kind of nonlinear superpoly called superpolies with balanced variables, and in this form. And I believe there are lots of superpolies in this form, so they are not hard to find. And we call the cubes whose superpolies have balanced variables as valuable cubes. So our contribution is that we propose a new heuristic algorithm to search for valuable cubes. And as applications, we improve the theoretical attack against the trivium and trivium when this paper was submitted in the last year. And we also improve the practical attack against the trivium, and which is still the best result now. Next, let's see the search algorithm briefly. To search for the superpolies with balanced variables in this form, we have got 4 ideas, and the last one finally worked. That is, we treat a set of cubes together in such that the common computation can be shared. And we also deal with a specific secret variable instead of recovering the whole superpoly. And we also reject hopeless cubes timely instead of finishing all the computations. And to reject hopeless cubes timely, we need the subset method, the divide and conquer strategy, and the 2 observations. And then we get the search algorithm. In the first step, we prepare a set of candidate cubes and choose a secret variable. And we divide the whole system into several subsystems by the divide and conquer strategy, and we solve each subsystem one by one. And during the computation, we remove the hopeless cubes in the first case, and we record the number of the cubes in the second case. And in the last, if there exists some cube such that the recorded number is odd, then we will get a valuable cube. And this is the algorithm. At last, let's see some applications. To provide a theoretical attack against the round-reduced trivium, it suffices to find one valuable cube with dimension no bigger than 78. And we have found many valuable cubes for 840, 841, 842 round trivium. And we also found two valuable cubes for 843 round trivium, which leads to a theoretical attack. And we also propose a practical attack against the trivium by finding more superpolys with balanced variables. And initially, we got about 200 valuable cubes, and we used the guess and determine method to solve the system. And all the computation can be done practically. Here are the details about the valuable cubes. And okay, that's all. Thanks for your attention. Hello?
Thank you very much. Are there any questions for this talk? In the room or online? No questions? Okay, so let's thank the speaker again then. Thank you very much.
I don't know why it doesn't work. Just
Let me
use
hello.
here, right?
Okay, thanks. So welcome to the third talk of this session, that it's Atom, a stream cipher with double key filter. It's a work by Subhadeep Vanik, Andrea Caforio, Takanori Sobe, Funkan Liu, Kosei Sakamoto, Willie Meyer, Santanu Sarkar, and Subhadeep is giving the talk. Thank you.
Thank you for the introduction. So I'll be talking about this stream cipher Atom that employs a double key filter and also has a short internal state. The question to consider over here is what a stream cipher with a short internal state is and how is it different from a stream cipher with a longer internal state, for example. So in 2001, Birukov and Shamir published their seminal work on time memory trade-off attacks. And one of the main conclusions of the paper was that in order for a stream cipher to be secure against TMD attacks, the size of its state in bits must be at least 1.5 to 2 times the size of secret key in bits. And this was considered to be a rule of the thumb till about 2015, when Amnet and Mikhailov proposed a stream cipher Sprout, whose state size was actually equal to the size of secret key. And in spite of that, it seemed to be immune against the generic TMD attacks that Birukov and Shamir had proposed. Now, we all know that a stream cipher is basically a finite state machine. So we have this function f that maps a state to the key stream vectors of equal length. Now, cryptanalysis in this instance reduces to inverting this one-way function over any of these points Ci that the attacker has access to. Now, the algorithm that Birukov and Shamir had proposed had a trade-off curve of the form Tm squared d squared equal to n squared, with the limitation that T had to be larger than d squared, where Tm and d are the time, memory, and data complexity of the algorithm. Capital N is the size of the internal state space, and the offline complexity P is given by N over D. And now a typical point on this trade-off curve occurs when both the online and the offline complexity are n to the power 2 over 3, which is less than n. Now, if capital K is the size of the key space, and capital N equal to capital K, which is the size of the internal state is equal to the size of the key, then this, of course, is a valid attack because both the online and the offline complexities are less than K, which we understand to be the complexity of exhaustive search. So a rule of the thumb was to set N equal to K square. This way, it was not possible to find a point on this curve where both the online and the offline complexities would be less than K. So the main idea behind Sprout and other such stream ciphers with short internal states was that the update function would be such that it would require an additional information from the secret key to update the internal state. And as such, it's not possible to form any sort of map between the state and the key stream that does not additionally require the key as input. And so effectively, the state size of Sprout is 160 bits, whereas the key is only 80 bits, and so a generic attack can be prevented. Now, let me come to our construction. So the people who are familiar with the grain structure would recognize this kind of a structure. It's the basic grain structure, and our main design philosophy has been to react to attacks against Sprout and similar other structures, and to reason within ourselves how to best counteract, to come up with solutions to counteract known attacks. So our construction uses a 159-bit state and 128-bit key. We have a nonlinear register of size 90 bits, a linear register of 60 bits, and a decimal up counter which counts up to 511. And so initially the IV and some constants are loaded onto the register, and the FSM is allowed to execute for 511 cycles without producing a key stream. So after this, what happens is interesting. The two registers of 60 and 9 bits combine to form a single register of 69 bits, which is updated linearly. So the last 7 bits of this register, let's call this D, determines which bit of the key is added to this NFSR update function. And we also have a second key filter, K of T mod 128, which is also added to the NFSR update, and hence the name double key filter. So in the paper, we argue why both the key filters are necessary to guarantee security. Now, the first K of D filter is necessary to prevent attacks, the near collision attacks that was proposed against Plantlet, which had a similar structure. A near collision attack basically leverages the fact that two internal states with very low Hamming difference produce key streams that are heavily correlated. And by using this, the attacker can use algebraic techniques to recover the state in the key stream. So in Plantlet, it was proven that such internal states produce differential key stream that has 0 or 1 in 45 positions with probability equal to 1. But for Atom, this number is only 18 because of the additional key filter which updates the NFSR. And so this means that the attacker has to spend additional computational resources to ascertain whether the given differential key stream is the result of low difference Hamming weight states or not. And this kind of pushes the complexity of this attack to that required to solve 241 polynomial equation systems of high degree. And this is considerably higher than the complexity of brute force search. Now, in order to explain why the second filter is necessary, we propose a simple time memory attack on a variant of our construction that does not use this second filter. We show that a very simple time memory attack is possible because we can construct a map from state to key stream that only requires 7 additional key bits. And the algorithm that we propose in the paper has online time complexity of 273 minus t and offline complexity of 260 minus t, where t is a parameter used in the attack. And we show that for t around 60, both of these complexities are much less than the complexity of exhaustive search, and so the security arguments collapse. So the second filter kind of prevents any map of this type from forming. If we use this additional filter, we cannot make any map that maps the state to the key stream with only a few additional key bits as input. And in the paper, we go through a bunch of other standard security arguments. I'd invite the reader to go through for more details. And so here I conclude my paper. Thank you.
Thank you very much, Vadeep. Are there any questions in the room or online? No questions? No questions, no? Okay, I guess that's what happens in the session after the banquet. People are not really aware. So then we are going with the next speaker. I just stop sharing, right? Okay, thank you very much. So you should be able to share now. Thank you. Sorry, thank you again, Vadeep, for. Okay, okay. So the next talk is resistance of SnowB against fast correlation attacks in a work done by Jixin Gong and Bin Zhang, and Jixin is given the talk. Go, please, Jixin.
Okay, thanks for the introduction, and thank you very much for listening to my talk. I'm Xinxin Gong, and I will talk about our paper, Resistance of SnowB Against Fast Correlation Attacks. I'm sorry. Sorry, something wrong. I'm sorry, can I try again?
Yes, go ahead.
Is it okay now?
Yes, you cannot make it a bit bigger?
Okay, I'll continue. SnowB is a new member in the Snow family of stream ciphers, with two predecessors, Snow2 and Snow3G, whose linear attacks have been widely studied, based on bitwise or large unit approximations. The large unit approximation-based attacks give the impression that large unit approximations lead to larger SEI and also to better linear attacks.
Excuse me, can you put your slides in full screen mode?
It is not full screen. I'm sorry. Oh, sorry,
Or share your whole screen instead of an application.
Sorry,
You can try unsharing and reshare again, maybe, for doing that, right?
I'm sorry, maybe something is wrong.
Well, stop sharing and share the whole screen again.
Do you see the red button of stop sharing screen? On the top, normally, I think.
Is it okay now?
Perfect. Yes, thank you very much.
Yes, that's better.
Sorry. SnowB is with LFSR and the FSM structure. The FSM consists of 3 registers. For the updating, the operations like XOR, module addition, SBox, and permutation are used. To measure the strength of bitwise and large unit approximations, the concepts of correlation and SEI are often used, especially for m equals 1. The SEI of f is equal to its squared correlation. For our first contribution, we provide constant time algorithms to compute the correlations of 5 types of functions, which are used for the cryptanalysis of SnowB. For computing the correlations for type 2 and 3, we use existing algorithms from the following literatures. And for computing the correlations for type 4 and 5, we propose new algorithms by extending the slice-like techniques. The general idea of the slice-like technique is that first, divide the n-bit values into d-n-bit values according to the specific structure of the underlying function, and then pre-compute the connection matrices, independent of the input and output masks. And finally, compute the correlation by doing some matrix multiplications, which is a constant time procedure. Based on the above, we will analyze the bitwise approximations of some variants of SnowB. The first is SnowB sigma 0, where the permutation sigma used in the FSM updating is assumed to be identity. We consider 3 consecutive keystream outputs to cancel out the contributions from the FSM, and then obtain the bitwise approximation of the 3-round FSM, where 4 subnoses are introduced. The correlations of 4 subnoises can be computed as the products of the correlations of the introduced functions, which are all constant time procedures. With these computations, we found our best results with the SEI 2 to the power of minus 37.3. Compared to the designer's evaluation, which used bitwise approximations with the SEI 2 to the power of minus 58.7 to mount attack, we improved the fast correlation attack greatly by using our bitwise approximations. Next, for a new closure variant of SnowB, where the permutation sigma is used as proposed, and only one 32-bit adder used for updating the R1 register is replaced by 8-bit adder. As before, we construct the bitwise approximations and introduce 4 subnoises, among which the last 2 noises are new, where the permutation sigma is involved. Fortunately, their correlations can both be obtained with constant time complexities. Based on the above, we obtain our best approximations and also propose a faster correlation attack, which is less efficient than the brute force attack. Last, for another variant of SnowB, where both 32-bit adders are replaced by 8-bit adders, and whose bitwise approximations have been studied in the design document. Our contribution here is that we construct bitwise approximations with the SEI higher than that of the bitwise ones given in the design document, and the faster correlation attack can be improved accordingly. To sum up, although neither of our attacks threatens the security of SnowB, they fill a gap in the research on SnowB by considering bitwise approximations that have not been studied previously. That's all of my presentation. Thanks for your attention.
Thank you very much, Yixin, for the talk. Are there any questions in the room or online? No questions? There are no questions online either? Okay.
No questions online.
Okay, thanks. So let's thank Yixin again. Thank you very much. And the next talk is also going to be given by Yixin.
Is it okay now?
It's not a big, it's small as before.
Is it small?
Sorry?
Sorry.
No, it's.
Is it okay now?
Yes.
Yeah, I think it's very good. Thank you. So the next talk is comparing large unit and bitwise linear approximations of SNOW2 and SNOW3G and related attacks, also by Yixin Gong and Bin Zhang, and Yixin is also given the talk. Please go, Yixin.
Okay, thanks again. Now I will talk about our paper comparing large unit and bitwise linear approximations of SNOW2 and SNOW3G. I'm sorry, as introduced in the previous presentation, bitwise and large unit approximations have been used to mount linear attacks on SNOW2 and SNOW3G. So the question is, how do the large unit and bitwise approximations work for SNOW2 and SNOW3G? First, we reconsider the relationship between large unit and the bitwise approximations. That is, the SEI of a large unit approximation is the sum of the squares of all non-zero bitwise ones that are included in the large unit one, which shows that approximations on large unit alphabets have advantages over all the smaller unit and the bitwise ones in linear attacks. Then we compare the bitwise and the bitwise approximations for the FSM of SNOW2 and SNOW3G respectively. The first is on SNOW2. SNOW2 is with the LFSR and FSM structure. The FSM consists of 2 registers, with the FSM updating and keystream output as shown. For the bitwise approximations, table 1 shows the previous best 3 bitwise masks for 2-round FSM on SNOW2. For the bitwise approximations with the method in the literature, the XM15, the bitwise approximations of two-round FSM take the following form. To obtain the SEI of the bitwise approximation on any given TN mask, we need to compute the SEI of two subnoises. We have provided two slightly improved algorithms for these computations and found two more approximations having larger SEI. Then we compare the best three bitwise and bitwise approximations whose corresponding masks are listed in table 1 and 2 respectively. For each bitwise and bitwise linear mask with the same number, we have verified that the first coordinate of the corresponding bitwise approximation is exactly the bitwise approximation, and they have the same SEI. That is, each of these bitwise approximations is dominated by a single bitwise approximation. We know that correlation attack can be more efficiently implemented by using bitwise approximations. Improvement over the bitwise attack is natural for SnowB. Next, we compare the bitwise and bitwise approximations of Snow3G. Snow3G preserves all features of SnowB, but adds a third register to the FSM. For the bitwise approximations, we consider 3 consecutive histogramers to cancel out the nonlinear contributions using the linear masking method, and finally obtain the bitwise approximation of the 3-round FSM. For computing the correlations, we use the constant time algorithms in the following literatures. Our best 3 mask tuples are listed in this table, in table 3. For building the bitwise approximations, the general procedure is similar with that for building the bitwise ones, and the SEI computations are mostly similar with that in SnowB case. Table 4 shows the best 3 bitwise mask tuples we obtained for 3-round FSM of Snow3G. Then we compare the bitwise and bitwise approximations. Similarly, there are many cases that the bitwise approximations is dominated by a single bitwise approximation, and they have the same SEI. Based on the newly found bitwise approximations, we improve the fast correlation attack on Snow3G with all the complexities are bounded by 2 to the power of 174, while it is 2 to the power of 176 in the bitwise based attack. To sum up, although large unit approximations might have a larger SEI than all the smaller unit ones, for SnowB and Snow3G, however, there are many cases that the SEI of the whole thing is equal to the squared correlation of the dominating single bitwise approximation, and thus the linear attack can be improved over large unit approximation-based attack. That's all of my presentation. Thanks for your attention. Thank you.
Thank you very much, Yixin. So are there any questions? No questions in the room or online? Okay. Yes? Sorry, Stefan, what did you say?
No questions, I said.
Okay. Okay, well, thank you very much again, Yixin. Thanks a lot. And now we are going to start the last talk of this session, of this stream cipher session, which is improved guess and determine and distinguishing attacks on SnowB. And Yin Yang, Thomas Johansson, and Alexander Maximov are the authors of this work, and Yin Yang will give the talk. Please start. Thank you. It's not full screen yet. Can you?
Is it working now?
Yes, it's perfect. Thank you very much.
Okay, thank you. Thank you for the introduction. Hello, everyone. So my name is Jin Yang. So I will give a short introduction to our work, Improved Guess and Determine and Distinguishing Attacks on SnowB. I would like to start with confidentiality and integrity protection over the air in cellular networks, which protects the data transmission between users and base stations by encrypting and authentication authenticating the data. So in 4G, there are 3 such algorithms, which are Snow3G, Sook, and AES. So they are all used to provide 128-bit security level and are usually implemented in hardware to provide high speed. So now when we come to 5G, there are some new requirements on these confidentiality and integrity protection algorithms. For example, they should be able to provide a speed of at least 20 gigabits per second in software. And besides, they need to provide a 256-bit security level to resist against quantum computing. So based on such motivation, in 2019, we designed a successor of Snow3G cipher called SnowB for 5G use. So the picture shows the structure of SnowB, and Xinxin just gave the details of it, so I will not go into deep. But here I would like to mention that the linear part consists of 2 electrons, and we can regard the internal state as 4 128-bit registers like A0, A1, B0, and B1. Yeah. So since proposed SnowB has received some public cryptanalysis results as shown in the table. So in our paper, we proposed 2 guess and determine attacks with complexities below existing ones. And we also performed a linear cryptanalysis of SnowB, but of the reduced variant. So one advantage of our distinguishing attack is that our attack does not need long key streams. So for our guess and determine attacks, they are based on the observation that if a variable appears twice in an equation with nonlinear operations in between, then this variable may have 0 solutions. Then for these guess and determine paths that involve this variable, we can just truncate them instead of going deeper. So in our paper for SnowB, we found 3 such conflicting equations for A0, A1, and some another intermediate variable. So as shown in the figure for the guess and determine process, for example, at this guess and determine path, we found that A0 does not have any solutions. We just don't need to go to A1. We just trace back and go to some other guess and determine path. So in our paper, we have carefully designed the guessing strategies to truncate as many guess and determine paths at an early stage as possible. So with this idea, we were able to reduce the complexity from 2 to the power of 512 to 2 to the power of 378. So we also performed the linear cryptanalysis of SnowB, but we considered a simplified version in which the 32-bit adders are replaced by the XOR operation. So we tried to find some bias in 3 consecutive case-string words. So here shows the expressions. So B0, B1, and A0 are from the abstract contribution, and we found that they all appear twice. So it's possible to cancel them out. So we have introduced some linear masks and combine the bytes based on the permutation sigma. So with that, we can cancel the abstract contribution. Then we found a linear approximation, and this approximation can have 48 S-box approximations. So we found some linear masks to cancel as many S-boxes as possible. In our results, we were able to cancel out 9 S-boxes, and the resulting bias is 2 to the power of -303. And accordingly, we had a distinguishing attack of complexity to the power of 303. As I mentioned, our attack does not need any long key streams. And this is because the abstract contribution A0, B0, B1 all appear twice. And it's possible to cancel them out and explore a biased combination locally. While on the other hand, the last variable, A1, does not appear in the expression of the 3 key stream words at all. So based on this observation, we introduced one modification in the SnowBI cipher, which is a SnowB variant we proposed last year. maybe in 2020. So the picture shows the FGR part of SnowB and SnowB I, and the highlighted parts are the modifications. So the modification colored in red is relevant to our attacks. So specifically, we have moved the tab position of T2 from the lower 128-bit part to the higher part. This is exactly A1. So then in this case, A1 will appear in the output in the expression of the three keystring words, and it will appear only once. So now it becomes impossible for us to explore or bias the combination locally. Lastly, I would like to mention a latest result of SnowB. So in the Eurocrypt conference this year, there was a correlation attack against SnowB with complexity to the power of 240. So this is faster than exhaustive K-search. This attack has been reported to 3GPP, and in this 3GPP communication draft, it writes, 3GPP SA3 kindly asks Sage to assess the research paper mentioned above and determine any implications on SnowB. And subject to the outcome of the previous action, SA3 kindly asks Sage to proceed with the development of the 256-bit encryption and integrity algorithm specifications based on SnowB. So this indicates that SnowB might need to have some more modifications, but it can still be very promising for 5G use. So I think we can pay more attention. Okay, with that, I would like to end my presentation. Thank you very much.
Thank you very much. Are there any questions in the room or online?
So I may have a question on my own, if I may.
Sure.
So what happens when you have a long key stream, or is your Eurocrypt paper, does it use a long key stream, unlike the attack you presented here?
Sorry, you mean what's the difference, or what's the effect?
And especially, do you use a long key stream for that attack?
Well, in our attack, we don't need the long key streams, but actually in their attack, they need long key streams. So actually they are, yeah, but anyway, it's still an academic attack faster than exhaustive K-search. Yeah, so it's still interesting, yeah.
Thank you.
Thank you.
Any more questions? I had a small one because in your last slide, you talk about some other modifications. Do you have any ideas? What should that be?
Well, because I think because 3GPP asks Sage to make the corresponding modifications. Now I don't know about the progress because of the COVID situation, but we have some general ideas. But because it's not our task to make the modifications, so yeah.
But what ideas would you apply if you could? I mean,
I don't know if that's the basic idea is to like to remove these linear trails, but as for how to remove it, I don't know if it's allowed to say here because sorry.
Okay, no problem. Good. Thanks a lot. So no more questions. Then let's thank again Jin Yang and all the speakers of the session, please. Thank you.
Thank you.
Thank you very much. So we have now a pause until 10:30. Yes. Sorry? Leave, right? No, it's okay. Okay, so. Okay.
So just an announcement for people in the room. So the other ones, you can have a break. So I asked again what happens today with